Hierarchical Multiobjective Shortest Path Problems. Presentation for Wafer 2020. Let us begin with the classical shortest path problem. Consider a grid where some cells are free and others are blocked. These are marked in gray on the figure. Suppose we have a robot that can move from cell to cell in either of the four directions. And let's say we have a goal cell that the robot needs to reach. Finding a shortest path from robot's current position to the goal is an instance of the shortest path problem. More abstractly, we can formulate it as follows. Given a graph G with two distinguished vertices, called the root and the goal, and a cost function C, which assigns a non-negative real to each edge, we need to find a path from the root to the goal that has the smallest cost, where cost of a path is defined to be the sum of costs of its edges. Shortest path problem is a classical object of study in motion planning, and a variety of effective algorithms exist to solve it. What if our cost value cannot be modeled by a single real number? For instance, what if our objective is to find a path to the goal that stays as far away from all the obstacles as possible? Since there will typically be many paths that optimize that objective, let us say we would like to find the shortest one among them. The multi-objective shortest path problem naturally fits into the same framework as the classical one if we redefine the type of the cost function. In our case, cost of an edge is given by a pair, AB, of non-negative reals, where A is the distance from the edge to the obstacles, and B is its length, which for the grid graphs is always equal to 1. In order to define cost of a path, we need to define a composition operation, which here takes the minimum of the first components and sums the second components. Cost of a path then becomes as follows. The first component is the minimal distance to obstacles, and the second component is the length of the path. Finally, we define an ordering on pairs, which corresponds to optimal paths having the smallest cost. Such a structure in costs allows us to run many classical shortest path algorithms, of which Dijkstra is perhaps best known. In some instances, it will succeed and produce an optimal path from robot's current position to the goal. However, for other locations of the goal cell, it will produce a suboptimal path, shown here in white, while a path of the smallest cost is marked in yellow. Both of these paths come equally close to the obstacles, but the optimal one is shorter. Indeed, the length of the path found by the Dijkstra algorithm is 18, while an optimal one has length 12. Perhaps the best way to explain why the Dijkstra algorithm fails is by alluding to the failure of the Bellman optimality principle. Being a dynamic programming algorithm, the Dijkstra relies on subpaths of optimal paths to be themselves optimal. More careful analysis shows that it is enough to know that there is an optimal path whose all initial segments are optimal. But even this weak form of the Bellman principle fails for our cost structure. Indeed, consider the cell marked in yellow through which both of the paths we looked at earlier go. The cost of the white segment is smaller than that of the yellow one, since it stays further away from the obstacles. However, once juxtaposed with the same segment to the green cell, the ordering on the costs of combined paths flips. Note that a similar phenomenon will therefore impact any other shortest path algorithm which, like Dijkstra, consists of a single wavefront propagation. To describe conditions on the cost structure under which the Dijkstra algorithm does work, we need the notion of a cost monoid. Recall that a monoid is a set with an associative binary operation, referred to as multiplication, and a unit element. A cost monoid is a monoid with a linear order which respects the multiplication in the sense that if a is less than or equal to b, then multiplying both sides by any element C preserves the inequality, and with the unit element being the smallest element in this order. We have already encountered two examples of Cosmonoids. The most familiar one is the non-negative reals with summation. This is the Cosmonoid that is used most often in motion planning. The other example that we have seen before is R-min, reals with the operation of taking the minimum. Note that in order to have a monoid, we need to add the infinity element, which becomes the unit element under this operation. And note that we reverse the ordering compared to the usual one on reals, so that infinity becomes the smallest element. A closely related closed monoid is R max, where the operation is taking maximum, and 0 is the smallest element. Given two monoids, we can consider their Cartesian product, and if each monoid is endowed with a linear order, we can endow their product with a lexicographic order. It is important to note that Cartesian product of cosmonoids may or may not be a cosmonoid. For instance, the product of R plus with R min is a cosmonoid, while the product of R min with R plus is not. Note that the product monoid of R min with R plus with the lexicographic order is precisely the cost structure we encountered in the earlier example. Importance of the concept of the cosmonoid is highlighted by the following theorem, which appeared in the reference at the bottom of this slide. It turns out that the Dijkstra algorithm will always succeed in finding an optimal path between any two vertices as long as cost values form a cosmonoid. As a matter of fact, many other classical algorithms in motion planning will work with cosmonoids in place of positive real-valued costs, but this discussion is out of the scope of this conversation. Let us introduce the notion of a multicost, which stands for a Cartesian product of cosmonoids with lexicographic order. As we have just discussed, the class of multicosts is wider than the class of cosmonoids, and the Dijkstra algorithm may fail to find an optimal path in a graph weighted by a multicost. Such weights do appear naturally in the framework of minimal violation planning, and in particular in its application to autonomous vehicles, where regulations on minimal clearance to other road agents are naturally modeled by multicosts with R-min factors. In the rest of this presentation, we concentrate on the following question: how can we efficiently find optimal paths in graphs weighted by multicosts? Consider a very simple grid environment with a single obstacle cell. We're interested in finding paths from Robert's current position to the goal, which stays far from the obstacle as possible, where obstacles include the boundary of the grid. There are many different paths that optimize distance to obstacle. A convenient way to collect all of them is through the concept of an optimal subgraph, which is defined to be the union of all optimal paths. When the graph is weighted by a cosmonoid, we have a simple algorithm that finds the optimal subgraph. We begin by running the Dijkstra algorithm, but instead of stopping it once the goal is reached, we continue until all edges have been visited. This gives us cost to come. That is, cost of an optimal path from the root to the origin of the edge. Next, we run the Dijkstra algorithm backward, starting from the goal, which computes for us cost to go, the cost of an optimal path from edge's end to the goal. Once these values have been computed, it becomes very easy to determine whether any given edge belongs to the optimal subgraph. Already after the first run of the Dijkstra algorithm, we know the total optimal cost from the root to the goal. For a given oriented edge E, we compute the product of the cost of an optimal path from the root to E with the cost of E times the cost to go from the end of E to the goal. This quantity is always at least as big as the cost of an optimal path, and they are equal precisely when E belongs to the optimal subgraph. Note that the asymptotic complexity of this algorithm is the same as that of Dijkstra, for we run the latter twice, followed by a linear pass over edges of the graph. Let us take one more look at the optimal subgraph. Recall that we consider the paths from the route to the goal whose minimal distance to the obstacles is as large as possible. Since the optimal subgraph is defined to be the union of such paths, each edge in the optimal subgraph lies on an optimal path. Notice that in this particular case that you see on the board, any path within the optimal subgraph from the root to the goal turns out to be optimal. This statement is not automatic, for it is conceivable that multiple optimal paths can be combined into a suboptimal one. In general, an optimal subgraph is a directed graph. But in this particular case, since we're only concerned with the minimal distance to the obstacles, both orientations of every edge belong to the optimal subgraph. Here's another example where orientation does matter. Consider the shortest paths from the root to the goal. That is, cost of every edge becomes 1, and the oriented optimal subgraph is shown on the right. Once again, there are multiple paths within the optimal subgraph, and all of them have the same length and are optimal. Even though the graphs in these illustrations are rather simple, this phenomenon is general, and for these two types of costs, any path from the root to the goal in any optimal subgraph is itself optimal. This motivates the notion of a regular cost monoid, and our discussion can be summarized by saying that R+ and R-min, the two cosmonoids we use throughout this video, are regular. An interested viewer may wish to consult our paper for an algebraic characterization of regularity, as well as for an example of a non-regular cosmonoid. Empowered with this concept of regularity, we are ready to describe the main contribution of our work. Given a multi-cost S, where each Si is a regular cosmonoid, and an S-weighted graph G, we propose an algorithm for finding the optimal subgraph of G. We assume that the cost function is given by its coordinate functions, each taking values in a regular cosmonoid. Our algorithm iteratively passes to optimal subgraphs by looking at one coordinate at a time. Let us illustrate this on an example. In the grid, familiar from the previous slides, we're looking for the shortest path among those that stay as far away from the obstacles as possible. Our multi-cost S is the Cartesian product of R-min with R+. The algorithm begins with the whole graph G, and at the first iteration, we find the optimal subgraph of G relative to the first coordinate of the multi-cost only. In other words, we find those paths that stay as far away from the boundary as possible, regardless of their length. This is the graph O1. At the next iteration, we find the optimal subgraph of O1 relative to the second cost function. That is, we find all the shortest paths from the root to the goal among the paths within O1. In this example, multi-cost has only two coordinates, so the resulting graph O2 is the output of the algorithm. Notice that all paths within O2 are optimal with regard to the cost structure provided by the multi-cost S. In this video, we focused on providing the general description of our iterated algorithm. Numerous optimizations are possible. For instance, one may use heuristic-based algorithms to speed up the construction of the optimal subgraphs. Various early termination strategies are possible, etc. These are helpful techniques, but they will not change the asymptotic complexity of the algorithm, so we'll leave them for another time. We hope you have enjoyed this video, and thank you for watching.